Miller-Rabin algorithm. We say a number A is a witness for n being a composite if a power n minus 1 is not equal to 1 mod n. Okay, then we claim that A is a witness. Okay, we also have to assume that A is a group element, okay, meaning A is a member of Z star n. Okay. All right, that is one of the important properties of witness we talked about earlier. This is in the context of Fermat-Euler test. Okay, but in the context of Miller-Rabin, the definition of strong witness is a little bit more elaborate. So let's quickly recall what we did in the context of Miller-Rabin. We say a number A is a composite number if the number A power u, right, is not equal to plus or minus 1. All of these are computed in mod n, okay, and A power 2 times u, A power 2 square times u, this sequence of numbers all the way until A power 2 power or minus 1 times u. Okay, this is 2 times u, just to be clear. 2 square times u. So every term is the square of the preceding term. Okay, so we want all of these terms or these elements to be not equal to minus 1. Okay, then we claim that A is a strong witness for n being composite. Okay, the question now is, this is called witness and this is called strong witness, right? Can we talk about the scenario that if an element is not a strong witness, okay, can it be a witness? Okay, that's the question that I'm going to talk about now. So this is the condition for strong witness, right? Suppose we found out that element A is not a strong witness. Okay, what does that mean? That means that one of these conditions must be wrong, right? Either this is wrong or this any one of the elements in the sequence is equal to minus 1. Okay, this has to be plus or minus 1. Okay, so one possibility is that the A power u element value is plus or minus 1. Okay, once you have plus or minus 1, remember that every element in the sequence is just square of the preceding term. So all of this will be 1, 1, all the way until 1. Okay, now I'm going to also include A power 2 power r. Okay, remember the next term is after this term, what is the next term? Next term is A power 2 power r, right? So let's write the vector as follows. We have A power u, A power 2u, A power 2 square u, all the way until A power 2 power r minus 1 times u, and A power 2 power r times u. So this is our vector of sequence of elements, or if you want to call that way. Okay, the condition is that in order for A to be a strong witness, A power u should be not equal to plus or minus 1, right? It should not be 1 or minus 1, and all of these elements until A power 2 power r minus 1 times u should not be equal to minus 1. Okay, if n is prime, A power 2 power r times u will be 1. That's basically Fermat's Euler's theorem we talked about earlier. All right, and now let's consider the scenario that the number A is not a strong evidence or a strong witness. In that case, what can we say? In that case, this property must be false. So let's assume A power u is equal to either plus or minus 1. That's the reason why it's false, right? It should not be equal to that for a strong evidence. But if it is not a strong evidence, it can be equal to plus or minus 1. Once you get a plus or minus 1, what can you say about the entire sequence? All of these elements will be 1. Okay, remember this is a power 2 power r times u, just to be clear. Okay. What about the other scenario? Maybe the first element was indeed not equal to plus or minus 1. So we don't know what exactly is. Let's put a notation star. But at some point in the sequence, maybe we have sequence of numbers that are different from plus or minus 1. Suddenly at some point we get a minus 1. Okay, that's the reason why we say it's not a strong evidence, right? At some point this property must be false. That means it must be equal to minus 1 at some point. And then we will have all of these. Okay, right? Let me clarify one more thing. It is possible that the minus 1 occurs just exactly here, right? At this point, then the next element will be 1, so we can stop it. That's why I don't know exactly how many ones will come. That's the reason I put it like this. Okay, and now let's think about what it means in both scenarios. Okay, in the scenario that the first element a power u turned out to be equal to plus or minus 1, in that case, where are we ending? The last element is 1. Okay, which means the element a cannot be evidence from the context of Fermat-Euler discussion, right? An element can only be considered as an evidence if a power n minus 1 is not equal to 1. Okay, but you remember that 2 power r times u is nothing but, I have to recall that n minus 1 is nothing but 2 power r times u. We talked about it earlier, so I assumed you watched the other segment. Okay, that means this is going to be n minus 1. A power n minus 1 is equal to 1 in this case. That means it cannot be a witness. Okay, so if we have an element which is not satisfying the first property here, that means it will not be a witness. Okay, now let's consider the second case. At some point it has become minus 1, right? And then even when it is becoming minus 1, when you square it, it will become 1. Okay, the next term will become 1, which again tells us that the last element in the sequence will end with 1. Okay, so what did we learn so far? So far we learned that if an element A is not a strong evidence, okay, if A is not a strong evidence, okay, it doesn't belong to the set of all strong evidence, okay, then it cannot belong to evidence either. Okay, so if A is not a strong element, strong evidence element or strong witness, then we say A is not element of witness either. Okay, so two types of witnesses we are talking about, right? We are talking about witness, which is what we defined in Fermat-Euler, and then strong witness. This I should have been consistent. It's called strong witness in the context of Miller-Rabin. What I proved so far is that if an element is not a strong witness, that element cannot be a witness. Okay, now let's apply logic. What about the opposite then? If an element is indeed a witness, then we can say it must be a strong witness. Okay, now we can think in terms of set theory. This is strong, and this is just a regular witness. Okay, this is just a Fermat witness. Okay, so I call it F witness to show it. Fermat is here. Fermat witness elements are here. Miller-Rabin witness is a bigger set, hopefully bigger set. Okay, it cannot be smaller, that's for sure, that because we just proved it. So that's one of the reasons why we think that Miller-Rabin is better than Fermat-Euler, because the number of elements in the strong witness set is at least as big as the number of elements in the just the witness set you would get when applying Fermat-Euler relationship. Okay, if an element A is not a strong witness, that element cannot be a witness. Okay, which means that if the element is a witness, it must be also a strong witness, just applying the logic. All right, I hope that you are able to compare Fermat-Euler with Miller-Rabin.